In this video, we're going to review the parallel axis theorem. So the parallel axis theorem states that if the moment of inertia for an area is known about an axis passing through its centroid, so that is passing through the centroid of that area, then we can use the parallel axis theorem to find the moment of inertia of the area about a corresponding parallel axis. So for example, we have some shape here that I've already drawn, and this shape has some area A, and the centroid of that shape is located here, this blue dot. Now, we have an axis, the x prime axis, for example, that goes through the centroid, and we may already know the moment of inertia for the area about that centroidal axis. However, we might need to know the moment of inertia for that area about the x-axis itself down here. And so the parallel axis theorem is quite powerful in that it allows us to do that. And so we're going to consider how we can do that. So we are going to first off consider some differential element dA. Right, so dA is up here, and the moment of area for dA about the x-axis, not the x prime axis, but the this is given by d I sub x is equal to the distance from dA to the x-axis, which we know here is y prime, so that's this distance right here, plus dy, the distance from the centroid to the x-axis, squared dA. Now, that's just for the differential element there. If we want to find the moment of area for the entire area, then we would just integrate that expression. The entire area A, we would find I sub x is equal to the integral over the area of y prime plus dy squared dA. So we have here this integral of y prime plus dy squared, dy, that whole summation is squared, and so we can expand that term into three different terms. So I'll rewrite this as I sub x to an area integral of y prime squared dA plus 2 dy area integral of y prime dA plus dy squared times the integral over the area of dA. So we've expanded y prime plus dy, multiply that by itself, and we end up with these three terms. I'm going to say this is term 1, this is term 2, and this is term 3. And we're going to look at each of those three terms in turn. So what is term 1? If we look at term 1, we can see that this is already the moment of inertia of the area about that centroidal axis. And so this is given by what we would call this I sub x prime bar. So that's the first term. The second term is equal to because we know that the x prime axis, that's the centroidal axis, passes through the centroid. So it passes through the areas. So therefore, we have this this integral, the integral of y prime dA, which can also be written as y bar, the average distance of y dA. And we know that this must be equal to 0 since that average distance of y to the centroid is 0 because we're already at the centroid. So the third term is the integral of the integral over the area of dA, and this is simply the area times dy squared. So the area of that shape multiplied by dy squared. So dy is the distance from the centroid to the x-axis, which is the other axis that you're trying to find the moment of inertia about. So if we put this all together, equal to I sub x prime bar plus a dy squared. And similarly for the moment of inertia for the area about the y-axis, we can say I sub y is equal to I sub y prime bar plus a dy squared. So those are the formulas which define the parallel axis theorem. I'll just write out what they mean in words as well. Moment of inertia of an area about an axis, in this case the x-axis, is equal to the moment of inertia of the area about a parallel axis passing through the area's centroid So that defines, basically said this term and this term so far, plus the product of the area and the square of the perpendicular distance between the axes. So this becomes a very powerful equation that we'll use extensively in looking at the distribution of forces on surfaces underwater.